His wife, Hilary Cane, who was a radio astronomer in her own right, gained her PhD from the university here in, I think it's 1978.
That's right.
1978, yes. So both Hilary and Bill have had a career in radio astronomy.
I didn't, actually.
And Bill had his own radio telescope on Bruny Island, but it's not let me steal all thunder. I'd like to welcome Hilary. Hilary retains an honorary research position at the University still. So would you welcome Hilary Cane?
Since I don't know what all your knowledge is, it's very difficult to know what level I should pitch it. So if I'm telling you stuff you already know, I'm sorry. And also I haven't actually been officially an astronomer for 40 years. I've been working in space physics, so it's a little bit different. So the electromagnetic spectrum, as you probably know, spans a very large range, and most of what you're doing is the visible way in there. And the radio is very long wavelength. And this shows you the actual wavelength, and most of the electromagnetic spectrum we don't see on Earth because we're shielded from it by our atmosphere. The radio spectrum is the biggest, actually longest range of wavelength that is accessible from the ground, and low frequencies is long wavelength, and the number is approximately 1 metre. So I'm mainly interested, or Bill was, things happening at wavelengths longer than a metre. I'm trying to introduce a bit about radio astronomy to begin with. So radio, how do we get radio waves? There's a number of ways, but the synchrotron emission is most important for low frequencies. And that's because the emission mechanism is such that the intensity gets more intense as you go to lower frequencies. Sort of objects that you would see are supernova remnants, radio galaxies, clusters of galaxies, and also planets. So synchrotron emission is when you have cosmic ray particles spiraling around a magnetic field. So the ones that mainly that are producing what radio astronomers are looking at are cosmic ray electrons, so they're relativistic. They're called synchrotron radiation because the optical emission that they saw was that mechanism in synchrotrons. There are other mechanisms as well, but they're not so important at low frequencies. Get thermal emission, and that's from ionised gas in H2 regions. At low frequencies, you can actually see the H2 regions because the synchrotron emission is absorbed in them. So you can actually, if you look at the galaxy, you see emission from the galaxy, which is synchrotron, and then there's these holes in it, which are because there's H2 regions that are absorbing the radiation from behind. Radio astronomers also study spectral lines. The one that was of most interest originally was H1, and that was actually looked for. They knew that they got continual emission, and they started to look for lines, because lines tell you if you can get velocities from lines, so they're very interesting. Nowadays, of course, they see lots of molecules as well. This is all not at low frequencies. There's also plasma emission, and that's from the sun. So they're the main 4 mechanisms that we know to produce radio emission. So this is the Parkes dish, which is what most people think of a radio telescope. But the trouble is that to get good resolution, which is what you want to be able to see features in things, the resolution goes as the wavelength divided by the diameter of your dish. So if you're going to long wavelengths, you end up with dishes that are impossible. So at very low frequencies, you can't have single dishes. So what radio astronomers do is they make arrays of telescopes to get the effect of a big dish. This is the very large array in New Mexico, in the United States. So I just going back to low frequencies. Low frequencies wasn't studied very much. In fact, Tasmania has a part to play in that. Very low frequencies have been done from the ground in Tasmania. And the reason that it's hard to do is because the Earth's ionosphere cuts out the radio emission at very low frequencies. So typically most people would say that you can't see below 20 megahertz from the ground, but in fact in Tasmania there have been observations made at 1 megahertz and 2 megahertz, but it's very hard to do. The other problem at very low frequencies, and this is what the main reason why nobody did much at low frequencies for a very long time, and that's because the ionosphere changes with time, and I'll come back to why that's a problem. The other big problem with doing low frequencies is man-made interference. It's absolutely dreadful. You get it from all kinds of things, like, I mean, even fish tanks and bad insulators on power lines. It's really, really hard to observe at low frequencies because of man-made interference. So now I'm going to tell you a little bit about the history of radio astronomy. It was the date that you will read in textbooks is 1932, when Karl Jansky, he was looking at lightning really, and when he analysed his data, he could see there was this hiss, and he didn't know what it was, but later on he found out that it had a sidereal period, and that and as I said further down, he determined that it came from the centre of the galaxy. But Bill was actually born before that, so his whole lifespan started before radio astronomy started. He was an American, and he was born just by chance in Illinois, by chance in that his family lived north of there, and his father was posted down there for like 2 years. And then in 1938, Grote Reber, whom some of you have heard of, I'm sure, most of you, he decided to look again to see more about where this emission was coming from. And he thought it would be like a black body, so that it would be at higher, if he went to higher frequencies, it would be more intense. So whereas Jansky was at 20 megahertz, Grote looked quite high, I think like 600 or 900 megahertz, and he didn't see anything. And then he went to lower frequencies, and he finally was able to see it as well in 1939. The sun was found to be a very big source of radio emission, and that was in 1942, which most of you will realise was during the Second World War, and the people who were working with radar thought that the Germans were trying to mess up their equipment, and actually it was a big solar burst. Then in 1944, Reber produced a map of the northern sky at 160 megahertz, and by 1955 they knew that what some of the sources of radio emission were. And Bill's PhD was actually in 1956, so he was right in there, and at that stage they weren't really sure what was producing this radio emission that Jansky and Reber had seen. So his PhD thesis was looking into a mechanism for producing that radio emission. And then in 1958 he got a job in California, and this is a picture that people like to see. This is a place that he went to. It's called Clark's Dry Lake in California. And this was his first trip there, and what he found was a very huge dry lake. It was very flat. In fact, he used to say it was kind of interesting because it was so flat it didn't even have earth curvature. And the important thing about it as well, besides being a big flat area, was it was completely surrounded by mountains, which meant that at low frequencies you could block out a lot of the interference because with the mountains. So that was in 1958. This is just to show the geography of all this. So Bill was born up here in Duluth, Minnesota, on Lake Superior, and his father, as I said, was posted down in Chicago briefly. So he happened to be born there, but both his siblings were also born in Duluth, and his father and his mother were all born in Duluth as well. Clark's Dry Lake is almost on the Mexican border. In about 1960-ish, the Convair that he worked for decided that they couldn't really afford to do this kind of research, and so Bill persuaded the University of Maryland to take it over, and they had offered him a job as a lecturer. So he worked there from 1963 to 1988, lecturing in astronomy and physics. However, before he went to Maryland, he was invited to go to the Netherlands, and you've probably all heard of the Oort cloud. This is Jan Oort, and this is Bill, 1962. Jan Oort was first person to say, if we could get radio lines, this will be really good. So he asked one of his students to work out where a line would be, and that student predicted this H1 line that I mentioned. That's neutral hydrogen, and it's at about a gigahertz, so it's much outside the range of what normally low frequency radio astronomers would look at. But Jan recognised that Bill's capabilities in antenna design was really good, so he invited Bill to come over there and help design an instrument where they could do a lot of mapping of H1. However, just before that, the Australians and the English had worked out a better way of building radio telescopes. So the telescope that they were going to build, which was called the Benelux Cross, and it was going to go through Belgium, the Netherlands and Luxembourg. It was going to be this huge thing. They never built it. They built a different one later on. But once again, this is pretty historical picture, because Jan was an extremely important and very highly regarded astronomer. I wasn't actually going to show this, but anyway. This is just showing you frequency and resolution, and how if you wanted to get minutes of resolution, nowadays of course people at even radio frequency get much better than that, but when this picture was made, so 300 at 10 megahertz, you'd have to have this huge aperture. So as I mentioned before, to get decent resolution at low frequencies, you build arrays of telescopes, and one of the arrays was the Lanherne array, which was in Tasmania, which is actually what I used for my PhD, is I worked with the Lanherne array. This just lists the various countries in the early days who actually did do observations at low frequencies. So when they built arrays, they're not made of dishes. I showed you the VLA, but at low frequencies you don't use dishes, you use antennas, and there are various kinds of shapes. This is called the UTR-2, which is in the Ukraine, and that's their individual element. It's that very peculiar shape like that, and that's because a simple dipole only responds effectively to one frequency, and what you want is a broadband dipole. So the dipole will go through a range, and that's what the Ukrainians invented. So this is Bill here, and this person here is the Ukrainian father of radio astronomy, and Bill and he finally met in '94. They'd been communicating for years, but of course Browder, his name's Browder, he wasn't allowed to really interact because of the communist state and everything. So this is another kind of individual element that you might put in an array. This is a log periodic antenna, and this is Bill also at Clark Lake. You can see how dry it is. This is in the desert. You've probably all heard of Death Valley. Well, the Clark Lake is in another valley a bit south of Death Valley. And the final instrument that Bill built had as its individual element this thing here. They called them a teepee because it looks a bit like an Indian tent, and it's basically a spiral antenna. That antenna was actually also used by the French. It's Bill's design, but the French used it as well for a solar and a Jupiter array. So this is, again, there's Bill there in France with that kind of antenna that he invented. This is just his own sketch. So it's roughly 720 of those TPs in a T shape, and then they were in banks. This is just sort of showing you the electronics of it, which I can't really explain to you, but anyway. And an aerial photograph of the instrument. So this is the north-south arm and the east-west arm, with the buildings over here. That's the edge of the dry lake, and beyond that it's just cactuses, and every time we went out there I would say to Bill, but there are snakes, and he'd say, I've never seen a snake, but every time I went out there we would see a rattlesnake or something like that. But the other thing that was interesting is because it's the desert, there were coyotes, and the coyotes would eat some of the cables off the antennas, but they only liked the red ones. it's amazing what astronomers had to, this kind of astronomy, how you have to deal with the wildlife. At Kilgura, when they had the big radioheliograph, they used to have galahs that would do wheelies like that and break the cables. And when I was working at Lanherne, our big problem was they put the Lanherne array in the middle of a cow paddock, so if any of the wires fell on the ground, then the cows would drag them for miles. And this is just another picture of the TPT. So he worked at Clark Lake for 30 years. This is just some data that came from it. A radio astronomer has a number of ways or different formats that, or different ways of presenting the data depending on what they're doing. But typically they make maps and content maps. Nowadays they make them, you know, with technology the way it is, very coloured and pretty, and you look at it and you wouldn't know whether it was an optical image or a radio image because it's been doctored. But typically, you know, the basic data is contours showing, you know, intensity as a function of position in the sky. So this is an 80 megahertz map of the galactic centre, which at the time that was unidentified. And whole lot of, this is just one field with all these different images or different objects in there. Unfortunately, the observatory was funded by the National Science Foundation, and it was really only, it was very small in the sense that just two scientists. So one person did all the solar stuff, and Bill used to say he did the rest of the universe. But so there were a lot of students, well, no, a few students. The real problem was that the place was not the best, easiest place to live because you're out in the middle of the desert, and even though it's a dry lake, it wasn't always a dry lake. And once that dried out, the mud would stick on your feet. So, but most of the time it was a dry lake, and in fact it was so dry that Bill used to fly. He used to live in San Diego and would fly across the mountains and by plane, and he could commute to work because his sons were going to school. And this person here was his engineer, and he also would fly, so they jointly owned the plane. What was interesting is this person here, this is Arthur Watkinson, who was at the University of Sydney, but he also was working for the Benelux Cross in the Netherlands. So he and Bill met in the early 1960s. But you know, one was an American and one was an Australian. But so well, I'll come back to that. But anyway, so there they are at Clark Lake. So as I was saying, the observatory, they stopped funding it in about 88. So Bill said he didn't want to do administration, so he decided to retire. And so we came back to Australia to live, to Bruny Island. But we didn't want to give up science altogether, so we went backwards and forwards for 20 years. We would spend 4 months every year in the United States. And what Bill was doing then was advising people at various institutions about how to progress with antenna design to do radio astronomy at low frequencies. One of the things that he did was persuaded them to build a 74 megahertz system on the VLA, which prior to that only started at a gigahertz. And then in about the 1990s, he thought it would be interesting to build something on Bruny Island just to see if he could do a better job of getting rid of all the interference. So what he did was, initially he just had a standard antenna, which was a log periodic antenna, and he mounted it on a big tower. And this is Arthur again. So once we moved back to Australia, Bill and Arthur could see each other again, and they would do projects. So when Bill was mounting this big tall tower to put the log periodic on it, Arthur was there helping him, so that was good. But the log periodic was huge, as I said, at low frequencies. So Bill developed a different antenna that would do the same job. And it's a kind of it's a dipole, but it's a fat dipole. And it operated from 6 to 60 megahertz, and it was running from about, actually a bit earlier than that, in about 95, I think. And with a simple dipole like that, of course, the only object that you can really see is the sun. And since I was a solar physicist, I helped do some of the science, but Bill's aim was to see if you could get rid of the interference by using your software. So what he would do is observe with a spectrum analyzer 1,028 channels, and then using the computer you'd pick up those channels that had the lowest signal, which meant they had the least interference. So basically you only use 10% of your data, and it worked reasonably well. So we says that there. So we actually, even though it's a simple little dipole looking at the sun, there was some interesting science that could be done with it because it went to low frequencies. These standard solar observations made all over the world, just monitoring the sun because we're interested in solar events that affect us on Earth, they typically stop at 25 megahertz because of this ionospheric cutoff. And back in the 70s, there was one instrument in space that was looking at the sun, but the most important one was launched in '95, but it didn't start till 14 megahertz. It went from 14 megahertz and down, and then even lower because you're above the ionosphere, you haven't got that cutoff. So that was an instrument called WAVES on the WIN spacecraft. But its top frequency was 14 megahertz, and most of the other ground bursts were 25. But BIRS, the Bruny Island Radio Spectrometer, would fill the gap. So we were able to do some, what I thought was important science, because of having that gap filled. The data itself was available on the internet. I mean, this put Bruny Island, Tasmania on the map. The Bruny Island Radio Spectrometer data was put up on the internet as it happened. But then, so that just ran more or less by itself, and meanwhile Bill started doing some more work on building antennas. So here he is, this is in our garage at home on Bruny Island with this different kind of antenna. So one of his students was very interested in building an array that had lots and lots of these elements, and so the Navy that he worked for would send like crates of stuff to Bruny Island, electrical stuff. I'm still trying, if anybody wants any electrical stuff, I'm still trying to get rid of it. I had boxes of all kinds of stuff and different things to monitoring radio stuff, all because Bill was working for them to try and move on with radio building something for the future. And this is the design that you can see it's a little bit different. I guess it's just to save money because his was solid aluminium. You could do it with the same way like that. So this is called the Very Large Array, and it's located also where the VLA is in New Mexico, and it's got 256 of these antennas, and it's doing observations. And the people who started it, would say that it's because of Bill that they could do something like this. So, as far as astronomy goes, this really is, to many people think, is the last frontier to go to low frequencies. But so there's not only is there the LWA, but there's also LOFAR in the Netherlands, similar kind of thing. This MWA, the Murchison Wide Field Array, is in Western Australia, and I think it's somehow or other part of SKA. I think you've heard about SKA. So there's 4 instruments now. I mean, Bill was like it by himself practically with Clark Lake in the 80s, and now there's big consortiums all over the world doing what he was almost going able to do. And the kinds of things they're going to be looking at is what I said before, supernova remnants are a very obvious thing to do. The other thing I didn't mention is transients, like things that you don't even know what they are. And there's this thing that I heard them talking about but didn't really know what it was, but still don't really. Cosmology to me is I don't know what, but this thing they call the epoch of ionisation. And the idea is that H1 line I told you about before, that's at 1 gigahertz, if it has this humongous redshift, it'll end up being at about, I don't know, a few hundred megahertz or less, or maybe even 100 megahertz. So these people who are now into low frequency radio astronomy, that's one of the major things they're interested in, is to try to find this background emission that would be from the very, very early universe. And of course, the other thing that, which is really where I fit in, is space weather, which is a term that we use for phenomena coming from the sun that affects the communications, gives you aurora, geomagnetic storms, whatever. That's what we call space weather. And that's also something that you do at low frequencies, because most of the stuff on the sun, the solar emissions from the sun are what we call plasma radiation. And the plasma radiation, the frequency that you get is basically proportional to the density. And so with the densities close to the sun, the sort of emission you get is around about 100 megahertz. So low frequencies is good for space weather as well. And then this is my final picture, which is in 2005 here in Tasmania, when Bill was awarded this medal. And the three people with him are three of his students, three people who did PhDs with him, who are, really at the forefront of what's going on in low frequencies in the United States. And they were here for that meeting. And one thing that Bill always felt, that something he was very proud of, was the fact that his students had done so well. And so that's where I'm going to finish. Thank you.
Any questions?
Will low frequency astronomy disappear because there is a modification of the ionosphere by our own low frequency transmissions, where the electrons are being ionised by ordinary radio stations? I believe there's a resonance set up between Van Allen belt and the Earth, causing this ionisation. Will that eventually cut off any low frequency research?
Well, I suppose it could, but it also depends on where your observatory is, because the ionosphere, you're not affected by the ionosphere. Well, I guess what you're saying is you think the whole ionosphere could be. Yeah.
Is the reason Tasmania was good place for astronomy the fact of the old hole in the ionosphere?
Well, that was why Grote Reber came here. What he did was this is some of you probably know this, the F0 F2 value. It's a megahertz at which the ionosphere starts to completely absorb things. And he said yes, there was a hole in Tasmania, but I don't know that. I mean, the hole, it's not really a hole. I mean, it's basically F0 F2 values are low at mid geomagnetic latitudes. And I think part of that is part of the reason why Tasmania is good, because geomagnetic latitudes everywhere else is in the middle of the ocean in the southern hemisphere. So, but I don't think nobody else has ever gone to such low frequencies. As I said, Grote Reber made a map of the galaxy at 2 megahertz. I made one at 3.7, but nobody else has even tried from the ground. So, yeah.
Do you know why the lantern aerials were dismantled or experiments were?
Well, I think basically they'd done what they were supposed to do. Yeah, I mean, the trouble with all those things, that the resolution compared to what people are doing now is just hopeless. I mean, like 10 degrees. Nowadays people are looking at arc seconds of resolution at these kind of radio waves.
The lantern site is where the airport is now?
No, if you're going out to the airport, and you've got that straight stretch before you finally do the thing, and the golf courses over there, it was in the paddocks off to your right. So it's still paddocks where the instrument was. Yeah.
Wasn't there one also at Henna?
Yes, yeah, that was burned down in the 67 bushfire. That was a 10 megahertz one.
Is it somewhere near?
I don't know where it was. That's even before my time.
Because there's a place there that looks awfully.
Yeah, no, there was one at Penna.
Candidate to me for
Yeah.
an array.
I don't quite know why they chose the airport. You would have thought there'd be lots of radio interference there, but I think the biggest problem is to find a big and flat enough area. Yeah. I mean, at Clark Lake was perfect, very flat.
Does Bill's research tie in with Grote Reber's research at Poplar?
No, not really. I mean, Grote did the galaxy at low frequencies, but he didn't do anything beyond 68. Nothing useful from an astronomy point of view. Bill never did mapping at that low frequencies. So they knew each other, but they never did anything together scientifically. I've actually got a recording that I got quite recently of Grote and Bill conversing. One of Bill's students, a guy called Tom Kuiper, came out to visit us in 1990, and he wanted to meet Grote Reber, so we took him up there, and Tom recorded it, and he sent me the tapes like 6 months ago. So I've actually got tapes of Grote and Bill talking, which I gave to the university if they wanted to put the ones with Grote out at the Grote Museum, Reber Museum.
Just in passing, Grote Reber, I was a member of the society back in the early 50s,
Mm-hmm.
and Grote Reber used to come to our meetings. Many times he came to our meetings, and he would often talk and
I'll bet he did.
great raconteur.
Yeah.
There's marvellous stories about his researches.
Yeah, he was a brilliant engineer. I mean, he basically, he was the first official radio astronomer, because, as I said, Jansky was an engineer and he had a job to do, and once he found he wasn't, he would have liked to have done more, but the people he worked for put him on a different project, whereas Grote did it off his own bat, paid for it himself, built his own telescope, worked out he did it the whole lot. I mean, he was a brilliant engineer.
Any last questions? Well, I just had a Richard comment, very interesting. I must confess to being totally ignorant of the expertise that was down at Bruny Island, the work was being done down there. And I grew up I found this evening's presentation fascinating. And it's given me a whole new picture of that part of the radio spectrum and how to deal with it and how to research it and the opportunities there. And it's interesting that we've heard the story of the pioneers.